Hi everyone. Just before we start, I'll get a show of hands. Who's played with neural networks? Yes, so a few of you have had some experience. So most of you haven't really done much with them at all. I'll talk quickly about what it actually is. And probably the best way to start is to compare it with traditional programming, which is we basically do something like this. This is what we do most of the time when we're programming. And if you want to, say, write a web page to do something like this, calculate body mass index, at the heart of this is an algorithm that this kind of works out your body mass index. And essentially, we write that algorithm. We figure out what's the formula for this. We write it, and then we test it. And if it doesn't work, that means there's a bug in there. So we go back and think, what have I done wrong? We change it, we fix the bug, we test it again. But some kind of problems are really not conducive to that. So if you were to write a program to say, well, what handwritten digit is that? You could divide all that up into pixels, and now you've got a big array of pixels. And how do you write an algorithm to figure out what number that is? And this is where machine learning can make this a whole lot easier. So the way a neural network works is, give a high-level overview. You've got something that looks like this. So on the input side, these are all the pixels. They would all end up in the input boxes here. And then we feed it into a network of artificial neurons. The design is loosely inspired by the way our brain works. And the idea with this is, to begin with, all of the internal weights and biases are set to small random values. So it won't work at the beginning, but we start out with a large set of training data, maybe 50,000 or more images. And we feed those through one at a time. So let's say we feed a 4 through that neural network. It's going to come out with an answer, and it's going to be wrong because it's not been trained. So then we say, what can we do to make it very slightly less wrong? Can we modify those weights and biases to make it a little bit more likely to be correct? Then we repeat the process with all of our 50,000 or so images. And when we've done that, we shuffle the images, change the order. That was called an epoch. And we do it again. We do another epoch. And we keep doing this over and over. Gradually, those weights and biases start to take effect. And then this can correctly infer what the numbers are. So we're going to build this in the next hour. But the question is, what's the advantage of building? Why don't we just use a library? Because there are a lot of libraries out there to do machine learning. And those libraries, there's nothing wrong with them. They're a great place to end up. They're a lot more sophisticated than what you could write yourself. And they're also faster because they use the graphics processing unit. The problem, though, is if you really want to understand the underlying principles, it's not a good place to start because they're all black boxes with lots of complex knobs and levers. You move a lever and it doesn't work anymore, and you don't know why. So it's not a good way to really understand them from the bottom up. It's rather like if you've ever flown a flight simulator. First thing you do is you start with something like this, right? A big passenger jet. But then you follow a tutorial on how to fly it. You get one thing wrong and it crashes and you don't know why. So you end up going back to something like this and really learning the basic stick and rudder skills and how to take off and land. And then when you got the hang of that, this makes a lot more sense because when you go through the tutorial, you've got these conceptual hooks on which to hang your knowledge. So we're going to not only fly this, we're going to actually build this as well, so really get to understand it. But before we proceed, I should make one word of warning, which is that we're actually going to be training 2 neural networks, right? So an artificial neural network and or the real human neural networks in your brain. So for the next half an hour or so, I've managed to break this down into something that's a series of fairly simple concepts. Training neural networks is actually fiendishly difficult to really get your head around But I've broken this down into a series of simple concepts, but it's essential if you want to understand that you pay attention for about the next half an hour while we go over those slides and don't get distracted. Otherwise, you'll kind of get lost quite quickly. So let's start with the basic concept, which is a neuron and what that is. So essentially, a neuron, it has one or more inputs, usually at least two. All those inputs have weights. There's a bias. And all of that stuff on the left combines to form a total input, goes through what's called an activation function, and gives you an output. Now, take a simplest example is called a perceptron. A perceptron has a comparator as the activation function, and it asks a simple question: is the total input greater than 0? If so, then it fires a 1, otherwise it outputs a 0. So let's give an example. Let's imagine this comparator has 3 inputs, and the weights are set as such, and the bias is set to minus 1.5. So let's run some numbers through that and see what we get. So imagine we have an 8, 5, and a 2. If we run that through, then we do that multiplication, but the inputs times the weights, we add in the bias, and we can see there we get 0.5, which is greater than 0, therefore this would output a 1. Right, that's pretty much as simple as it gets for a perceptron. So let's look at the state of a neuron. There's 2 aspects to the state. There's the long-term state, which comprises the bias and the weights. The long-term state determines its behavior. And then there's the transient state. So when the neuron actually fires, it has an output. And then there are the intermediate variables we have in determining the output, such as the total input. So let's see what we can do with this. Let's try and make a NAND gate, a simple logic gate, which has the following truth table if you assign off to 0 and on to 1. So not AND gate. Let's see if we can do that. And if we set the bias to 3 and the weights both to minus 2, without laboring through all the examples, that will work perfectly. Which means if we can build a NAND gate with a perceptron, you can build any other kind of logic gate just from NAND gates. So this is functionally complete. We can do anything just with perceptrons. But we could do anything before anyway. The interesting bit is how do we get this thing to learn? Because I put those biases and weights in myself. I worked it out. But imagine we didn't know that. We didn't know what they were. The interesting bit is, can this learn? Can it learn from examples what the correct bias and weights is in this case? So what we do is we start by initializing these values to small random numbers. These are actually quite big random numbers, but for the sake of the example, this works well. So we're initializing them as follows. And then what we're going to do is we're going to put some training data through there. So I'm going to put a 0 and a 1 in there. Let's see what we get. We get a 0 on the output because when we take the combined input, when we multiply 0 by 0.2 and add it to 1 times minus 0.3 and then add in the bias, we get a combined input of minus 0.4 in there. And that's less than 0. So this output's a 0, but the output we want in this case, 0 NAND 1, is a 1. So we've got the wrong result. So what we do is we ask ourselves, if we made a little increase or decrease to those weights of bias, how would that change the output? Would it make it a little bit less wrong? And the problem we've got here is if we make any small changes, nothing is going to change in the output, right? We have to make a really big change for anything to happen. So the problem is that comparator function looks like this. It's either on or off, 1 or 0. It's not conducive to learning. So what we can do instead, we can kind of soften that function. We can turn it into something like this, which is called a logistic sigmoid, which has sort of values in between. It has a gray area. So the other advantage is that when we start building networks of neurons and connecting them together, this outputs real numbers, right? Fractional numbers. So that makes a network, when we send fractional numbers to other neurons, a bit more rich and expressive. So this will work quite well. There is a problem though, because if you look at what the formula is for that, that's relatively expensive to calculate. Now remember that we need to be training this with tens of thousands and sometimes up to millions of training samples, and we may have thousands of neurons. So this isn't the best kind of formula for something that you want to calculate quickly. So over the years, people have experimented with simpler formulas to see what works, and they found that something remarkably simple does a pretty good job, called a rectified linear unit, or a ReLU. And it's actually much easier to calculate than to pronounce. So with this, if x is greater than 0, it's x. Otherwise, it's 0. Now, they've also found that in most cases, we can improve this. We can make a better version of the ReLU, called a leaky ReLU, by having it leak on the left-hand side. So if x is less than 0, it's x over 100. That's still really easy, fast, quick to calculate, and that works really well. So now we've got a neuron which outputs fractional numbers, real numbers, instead of whole numbers. So in the case of our NAND gate, we still need to interpret the answer in the end. Is it a on or an off? And to do that is really easy. So let's say it outputs a 0.2. We just say, well, 0.2 is closer to a 0 than it is to a 1, so we'll interpret this as off rather than on. If it was a 0.8, we'd interpret that as on. So we just look at whatever it's closest to. But the important thing now is that we can measure the rightness or wrongness of this. So if it outputs a 0.2 and we wanted it to an output of 0, we can say the error is 0.2. The error is the actual output minus desired output. If the desired output was a 1, the error would be minus 0.8. Right, so it seems reasonable that we want to minimize the error across as many of the samples as we can, right? But there is a complication in doing this. If we simply say, let's minimize the total error across all samples, we're not going to get a very good result. Imagine we've got 4 training samples. All of them have an error of 0.2. All of them, it's got it right. Remember, if the error is less than 0.5, it's basically going to get it right. So it's not a big deal. That's a good result, very good outcome. Imagine now, instead, we do the same thing. The first 3 have an error of 0. The last one has an error of 0.6. That's now got the last one wrong. An error of greater than 0.5 will get it wrong, but the total error is lower. Right? With machine learning, we make the rules, it follows them. If we say minimize the total error, it's going to favor that bad result over the good result. Right? So what we need to do is something to punish those big errors like 0.6 more than the small errors like 0.2. And the easiest thing to do is to square the error first. If we square the error before adding them up, then we're going to fix that problem. We're going to punish the big errors more than the small errors. So we're not minimizing the total error. We're minimizing something else, which we call the loss. The loss is the variable we're trying to minimize. And we can define the loss function however we like, but usually for categorizations, issues what we're doing now, it's the error squared, summed across all training samples. Loss is the sum of the error squared, where the error is the actual minus the desired output. Now, a couple of nuances. We could write this instead of half sum error squared identical, right? If you try and minimize the sum of the error squared, you're going to get the same result as if you try and minimize half of the sum of the error squared. The reason we favor the second one, it creates a nice mathematical symmetry that we'll see soon. Another point is that instead of putting sum, we could put average, and again, it would do exactly the same job. Loss is also sometimes called cost. Cost, loss, same thing. Now, here's an interesting point. We don't usually calculate the loss, which might seem weird. If we want to minimize something, surely the first thing you do is you work out what it is that you're minimizing. But you imagine, if you think of yourself as a good driver, you're constantly trying to do things to minimize the chance of an accident. And you might be quite good at that. But If I was to ask you, what is the chance of you having an accident, 1 in what, you're probably not going to be able to tell me, right? So you can take actions to minimize something without actually working it out. And if you look through a neural network for the code that squares the error to the loss, you won't usually find it. So let's go back now and plug that leaky ReLU into our NAND gate. So again, we start out with small random values. And this time, I'm going to plug a 1 and a 0 in there. So the combined input is now 0.3. Right now, in this case, the desired output is 1. The actual output is also 0.3 because when we put 0.3 through that ReLU, because it's greater than 0, then it's simply 0.3. It's a 1-to-1. So now the error is minus 0.7. So we can see just from the sign of the error that we need to increase the output to reduce the error and the loss. A small increase to the output will have a good effect. Can you see that? So simplest thing we can possibly say in this case is we need to increase the output to reduce the error and the loss. So that means we also need to increase the input. Why? Because we're on the positive side of the ReLU, right? We're aware. So the input and output are in a 1-to-1 correspondence. So we also need to increase the input, which we could do by increasing those biases and weights a little. So what we could do is, now that we've worked out what we need to do for this training sample, we could take all of the training samples and repeat the same calculation and get votes. We're saying how many training samples want to increase the input, how many training samples want to decrease the input, and whichever vote wins, then we make a little adjustment to the weights and biases, and then we repeat the process again. Now, that would kind of work. You can see intuitively that would help us gradually improve. But what we would be doing is minimizing the error, the total error, not the total loss. Right? We would not be punishing the big errors more than the small errors. Now, remember how important that is to get a good result. We've got to punish the big errors more than the small errors. So how might we do that? And it's quite simple, really. Instead of simply getting a vote to increase or decrease the output, we get a variable number of votes. The number of votes you get is proportional to the error. So in this case, the error is minus 0.7, so we get 0.7 votes to increase the output. Right? If the error was only minus 0.1, we'd only get 0.1 votes to increase the output. Right? So that way, the big errors are weighting much more than the small errors. Right? And we flip the sign because we're trying to minimize the loss on the error, not to maximize it. Right? So that means, again, we can say that the input also gets 0.7 votes. So what we could do now is we could take all of those training samples, work out the number of votes, and add those votes together. And then based on that, we can now make adjustments to the weights and bias. Now, that would work, and that's called batched learning. Right? We collate all the votes for a large batch or all of our training samples, and once we've got the total net votes, we then make the adjustments. But there is actually a slightly more efficient way we can do this called stochastic learning. So rather than collating all the votes up for all the training samples, we can update those biases and weights as we go along. As long as we make really small changes, we can make a change after every single training sample. That avoids having to do that collation. Right? So with stochastic learning, what we do is we take those 0.7 votes and we multiply it by a little factor called the learning rate. All right? In this case, it's 0.01. So when we adjust that, we get 0.007. So now what we do is we need to increase the bias by that amount. So the bias becomes 0.107, and we also increase the weight. So the first weight becomes 0.207. What about the second weight? We've not increased that at all, right? Why have we not adjusted the second weight? Right? It's because the input 0 for the second one. There's no point doing anything to that because it had no influence on it, right? So it could only do harm. We don't touch that, right? So before increasing or decreasing the weight, we multiply by the value of the input. Right? That also takes care of the scenario of this being negative. Imagine that was -1, that input. We would need to do the opposite. We would need to decrease the weight in order to increase the total input. Right? Does that make sense? Okay, so that, in a nutshell, is stochastic learning. This is how you train a neuron. We've almost covered everything. Right? There's one thing, though, that I want to touch on, which is that by doing this, we are actually minimizing the total loss, the square of the error. And even though we never worked it out, we didn't do any squaring, we're actually doing that. And I'm going to for the sake of interest, I'm going to explain to you how it is that we're actually now minimizing the square of the error. So if you can't follow this, it's not critical, but it is interesting to see how it works. So let's plot on a graph the input versus the error. So we had an input of 0.3 and an error of minus 0.7. Now you can see from this graph that if we increase the input a bit like we did, the error is going to go down. So now let's also plot this imaginary loss curve, this graph of the square of the error, the thing we never calculated, the thing we're trying to minimize. That's what it would look like if we were to plot it. Now there's a very interesting coincidence here, because if we look at what the slope of that is at that point, it exactly matches the error. It does that at every point in there. And we can prove this mathematically by differentiating the loss function. Right? That if you differentiate y equals half x squared, you just get y equals x. Differentiate that blue line, you get the green line. So we know that the slope is always the same as the error, and that means, remember, we took a little step to the right, proportional to that 0.7. What that means is that we're traveling down that blue slope at a rate that's proportional to the slope. Right? Imagine that that's a slide, that blue line, and you're sitting on that slide. You're going to start sliding down at a force proportional to how steep it is. This is called gradient descent. We keep taking a little step in proportion to the slope. Now, if we were doing batched learning, batched gradient descent, we will just keep going along that line till we got to the bottom. But because we're doing stochastic gradient descent, we change those graphs for every training sample. So we switch to a new training sample. Those are going to look different now, right? The error is going to be in a different place. So now let's say we happen to, for the next training sample, the error happened to be positive 0.35. That would mean we would know that the square of the loss function would have a slope of also 0.35. So that means that we would take a little step to the left, not as big as our last step, only half as much, right? Because we've only got half the error, right? So the votes corresponds to the negative error, which corresponds to the slope of the loss function. So you can see we've taken half of that step back because it was only 0.35. So we haven't quite ended up where we started. In fact, the position that we've ended up in is very much the same as the position we would have ended up in had we done a gradient descent on the combined loss for both of those training samples. If we added those two blue lines together and did a gradient descent on that, we would end up in pretty much the same place. Okay, so to summarize, stochastic gradient descent for each training sample, determine the slope of the loss function at the current position, but the error tells us slope. That gives us a number of votes, and we step the following amount minus the slope times the learning rate. And that's pretty much it to gradient descent. So let's build it. Now, there's two samples in this, and you can download those and work through those yourself. So from LINQPad, if you go to the samples in LINQPad and click download, import more samples, then if you scroll to the bottom, you'll see the samples for this training session. So They're all in there, so you can work through this yourself. Now, there's two samples. The first one is this NAND gate for the neuron. So this is how I've created a neuron. We've got 2 weights in there. I've hard-coded this neuron to have 2 weights. It has a bias, and we start by initializing these to small random numbers. That's it. That's all I've got for the neuron. Now, you're probably wondering why I've done this, but I've separated the neuron into 2 classes. It's good programming practice in general to separate your long-term state from your transient state. So I've created another class called firing neuron, which captures the transient state of a neuron firing, references the neuron, and has the output and that intermediate variable total input in there. And this is the method that fires a neuron. We take 2 inputs. The total input, we work that out. It's each input times the corresponding weight. That's exactly what we were doing to fire it. We add in the bias. Now we apply the activation function, right, the ReLU. So all we do is we say if the input is greater than 0, then we just take the input. Otherwise, we divide it by 100. That's all it is. It's a simple activation function. And this is how we learn the second one. First, to learn, we fire the input so we know what the output is and the total input. And then we work out those output votes, right? The output votes is the negative of the error, right? So it's just the expected output minus the output. That tells us how wrong we are and how much the output needs to change, or the output's influence on the loss. So then, remember, we need to multiply by the slope of the ReLU function. So I just want to go back now because there's something I wasn't quite explicit about, which is this situation. So the output here got 0.7 votes, and the input also got 0.7 votes. Now imagine that this input here was actually a negative number. So we're now on the leaky side of the ReLU, right? So what that would mean is the input would get how many votes? Exactly. We divide it by 100. The input will get 0.007 votes. So to work out how many votes to give the input, we take the output votes, we multiply it by the slope of the activation function. This is the chain rule in calculus. If you didn't understand the chain rule before, you understand it now. Okay, so there we are. We're multiplying by the slope of the activation function. Now, to the adjustment, we multiply by the learning rate, that small 0.01. And then we can now increase the bias by that adjustment. And we can also adjust these weights. Remember, we multiply the adjustment by the input. So if it's 0, it doesn't do anything. If it's -1, it flips it the other way around. So that's it. That's how we learn. The only other thing here is the code to do the training. We need to manufacture some test data, some data. So I won't go into the code. I do that with a LINQ query. It's probably easiest just to dump it out so we can have a look at what that looks like, what the training data looks like. So the data simply, we've generated a whole lot of random numbers here. And these are the inputs, and this is the desired output. So if the NAND gate is functioning properly, this is how it should work. We can manufacture as much training data as we want here. Really easy. So let's get rid of that. So that's first step is to manufacture the data. Second step is we divide it up into a training set and a test set. So I'm saying, let's take 80% of that data, and we're going to use that for training. We're going to put the remaining 20% aside for testing, because once we've trained it, we don't really know how accurate it is if we simply rely on the training data. It might got a very good with that training data, but not so good at generalizing to data it hasn't seen. So we have to put a separate set of data it hasn't seen, the testing data, to know how good it is. So then we train it for each sample in that training set. We call the learn method on that. And you notice I'm only going through that training set once. I'm only doing one epoch, because normally we would do lots of epochs. We would shuffle the data and do that again. But in this case, we have a limitless amount of training data. We don't need to do that. If we want more epochs, we can just make more training data. Finally, I'm doing a report on how accurate it was. So we're firing the neurons over the testing set, and then we're just seeing how many successes and failures we've got and what the error was. So we're going to run this now with 1,000 samples. So there's 800 for training, 200 for testing. And I've set the learning rate to 0.02. So let's run this and see what we get. Now, that's the final state of the neuron. It's automatically worked out from all of these training cycles that these are the right weights and biases. And it's got all 200 correct. So that has worked perfectly in there. We can also look at, I've also reported on the total error magnitude, and that's a histogram of all the errors that we've been getting. And because none of them are greater than 0.5, it means that none of them it's got the wrong result. So you can have a lot of fun with this and play with this. And because this is so simple, and this captures really everything there is to pretty much to training a neuron, you can learn a lot from this. So if we reduce the total number of samples to 100, we'll find that this will no longer work. So we've got 12 correct and 8 wrong. We simply don't have enough training samples to make this work. We need more than 100. We could also see if we change the learning rate to say 0.5, increase the learning rate too much. What happens if the learning rate's too big? It will oscillate, right? It will keep going. Imagine you're on that slide and you're sliding down that curve. You get to the bottom, you're going to go up the other side, right? So we oscillate. It doesn't work if the learning rate's too high. So you can experiment with all of this and see how well it works. You can also this is a NAND gate that we're training it to do, but we could quite easily make it do other kinds of functions. If I change this AND to an OR, it's now going to become a NOR gate. So we can see whether we can train it to do a NOR gate, and we can. That works just as well as an AND gate. But what about if I try to do an XOR in there? Can it do that? If I put an XOR in there, exclusive OR, doesn't work, right? Doesn't seem to be working at all. And we try this, it will not train. And there's nothing wrong with our training. The problem here is that you cannot do an exclusive OR with just one neuron. We need a number of neurons to make this work. Right, which brings us on to the next point, because right now I did promise that we would build a Cessna, but we've really only built a hang glider at this point, right? Because there's nothing really very exciting about a NAND gate. So what we need to do now is to turn this neuron into a whole network of neurons. So this is the architecture for a neural network. We have the inputs on the left. On the far right, we have a layer of output neurons. So in the case of, say, doing character recognition, each of those neurons on the right corresponds to whether it thinks it's that number. So if whichever one gives us the highest output, that's the answer it thinks it is. So that's the output layer on the right-hand side. In the middle, anything in the middle, we call those the input layers. So the idea is that every layer connects to the layer to the right of it. So it's hooked up as a directed acyclic graph. So the outputs of one neuron feed the inputs of another. Now, there is almost nothing else that we need to do that we haven't already done. And the process of training this, how do we train a network? What's different about training a network over a single neuron? We just train each neuron. So let's start with the firing of the network. If we want to fire the whole neural network, we go through each of these neurons in the hidden layer and we fire them one at a time. Then we move to the right and go to the next hidden layer, or the output layer in this case, and we fire each of these neurons in sequence. So we're moving from left to right when we're firing the network. That's called feed forward, when we're firing the whole neural network. And imagine we end up with these outputs. We look for whichever one is the highest, which is an 8. That means it thinks it's an 8. So we can see from this that big errors are going to be worse than small errors, just as with our NAND gate. So we would use the same loss function of error squared if we wanted to train this. So how do we do the training? How do we do the training cycle? And again, very similar to what we were doing before, We start by, with all our output neurons, we go through them one at a time, and we run that same calculation we did before. We work out the output votes, right? Which is effectively the slope of the loss function. So we work out the number of output votes, which is the output minus the desired output for each of these. Then we work out the input votes exactly the same way. Right? It's the same as the output votes if the input's positive. If it's negative, we divide by 100. That's the slope of the ReLU. Now, there's one extra step. We need to now go to the hidden layer. We go backwards. Right? This is called backpropagation. When you're training a neural network, the process of going from right to left is called backpropagation. So how do we work out the number of output votes in the hidden layer on these hidden neurons? How do we do that? And it's the simplest thing that could possibly plausibly work. The number of output votes you get on a neuron in the hidden layer is simply the number of input votes for all of the layer to the right weighted. It's the weighted sum of all of these input votes here gives you the output votes for each of these neurons here. That's the only extra bit of information you need to build a neural net. Right, so we're going to do this now, and I'm going to run through that example. Now, I won't labor through the source code. There's a lot more code here, but it's just plumbing. It's just hooking all the neurons up. There's only one piece of extra code here which we've not seen really in the next example that's actually related to the training of the training process, which is when we work out the number of output votes. So here we are. So when we're working out the number of output votes in the hidden neurons, we do that weighted sum. So we go to the layer to the right that we just processed, and we do a weighted sum of all of its input votes times the weight of that neuron. That's the only extra bit of code related to the actual process of learning. So we're going to start running this now. I will make one note on the fact that because we separated the transient state from the long-term state, what that meant is that we were able to easily parallelize this. So this actually uses all the calls on your processor, and it didn't take much code to do that at all. And there's just one place where we needed to lock for thread safety. So, okay, so let's run this now. The first thing we need to do is get some training data. There is a public domain database of training images. There's around 50,000 training images of handwritten digits and another 10,000 which are for testing, called the MNIST database. This sample automatically downloads them from the internet, so you're all ready to go. So we create a neural net. Now, the number of input neurons it has, they're not actually neurons, they're just inputs. Because it's a square image, it's the image width times the height, right? We're going to create one with 20 neurons in the hidden layer and 10 neurons in the output layer. Right, then I'm going to train this, use a learning rate of 0.01, and we're going to run this for 10 epochs. And then we're going to report on the failures, see how well we've done. So let's run this. So this is the first epoch. It's going through it for the first time. 93% so far, 95% with the second one, 95.2, 95.5. It keeps going up with each epoch, and eventually it kind of settles at the highest we're going to get. So we're up to now, after 9 epochs, we're up to 96.1% with the training data. That's the accuracy. Now, with the testing data, it's a bit lower because when we give it some data it hasn't actually seen, it doesn't usually do quite as well. But in this case, it's still got 95.4% accuracy, which is pretty good for 30 brain cells. Right? This is a home-baked solution with 30 brain cells, and we've got 95.4% accuracy with this. This is all a white box. This uses no libraries. You can go and have a look, understand it, and play with it. So let's look at the failures with the highest loss. So these are the ones it had the most trouble with, right? These are the digits. You can see you can see why that's quite hard to pick up. That one had a dot in it, that confused it. Okay, so that gives you an idea. I don't even know what that is. That's supposed to be. That's a 6, I think. It's done pretty well. So what we're going to do now is I'm going to run this again. I've written a LINQPad visualizer for the trainer, which means that you can dump it, and it dumps out a WPF control, so we can watch it learn. I'm going to run this again, and we're going to watch it as it learns. So this now is showing you the color indicates the bias. You can see the bias taking effect, and the color of all of these connectors indicates the weights. So we can watch the weights and bias as it learns. Right now, this is showing you the hidden layers and the output layer. It doesn't show you all of the inputs because there's too many. It doesn't show you all of the weights between the inputs and the hidden layer because there's too many of those. But it still shows you most of what's interesting. So we can now see what this kind of neural net looks like, and I've put in a pad where we can actually write a number in and see whether it works, because it's one thing just to run it over these test images, but it's another thing to actually run it yourself. So I'm going to draw a 1 in there. Oh, it thinks it's a 7. Let's try that again. Put another 1 in there. It thinks it's a 0. Now, when something like this happens, this is when you really learn what's going on. Right? How is it did so well with that test data and so poorly when we actually use it in practice? And when you look at all of those training images and test images, what you noticed is that all of those images are perfectly centered. Right? So, and when they scanned it in, part of the scanning, the handwritten, was centering. This is not centered. So it's got completely confused. Right? You can see there's no danger of this neural network taking over your jobs. So there are 2 ways that we can fix this. One of them is called data augmentation. What we can do is take our training set and deliberately shift them all around the place, scale them, rotate them, add some noise to them, and train those as well, and then it will learn how to deal with that. That's one approach. The other simpler approach in this case is we could do exactly the same thing to this canvas that they did to the training data, and we can center it before feeding into the network. And that's what I'm going to do. So I already did that. I just commented it out so you could see it fail. So now we're going to run this again. I don't actually need to retrain it, but I haven't written the code to save the training data. So it's only done 3 epochs, but it should now work. If I put a 1 in, that's going to get that right. And let's put something else. Put a 2 in. It's got that. Put a 5. It's already got that, even though we haven't finished the 5, right? So we've got up to fairly good training and test accuracy in there. But we can do better. So what we could do, there's a number of ways we can improve this. So one thing we could do is add an extra hidden layer. So I could put 30, click up to 30 neurons in there, and put another layer with 30 neurons in there. And let's see what happens. We are going to get a better result. But what you tend to find is that when you add more layers to this kind of network with this kind of problem, while in theory adding layers should always make it more expressive and powerful, it makes the learning much more likely to go wrong or to be suboptimal. So usually you find that for every kind of scenario where you create an extra layer here, you can probably do at least as well by putting all of those neurons into one hidden layer. Now this is not true in all cases, but with this image recognition, this character recognition, you can probably do just as well with just getting it into 2 layers instead of 3. So, but you can see we're up to 97.7% now just with our training score, 98 now. And let's see what the actual accuracy is with the test data. We're 97.1, so that's actually not too bad. We've got it even improved it even more. But we'd probably do just as well by putting all those 60 neurons into the input layer. The other thing I want to show you is what happens if we set that learning rate too high. So if I bump that up to say 0.005, you can actually watch the oscillation. Can you see the oscillation in the colors? So that's really useful, that visualization, because it immediately tells you if you've got a problem with the learning rate being too high. What I've actually done in this code is I've set it so that the learning rate automatically gets a little bit lower with every epoch. So as it becomes more accurate, it reduces the learning rate to prevent overshooting the ideal values in there. The other thing I'm going to do is we'll restore that learning rate. We're going to whack this up to, let's make it 100 neurons. And so we're still 2 layers, I'm going to put 100. And one of the things I've done with this, you can think of this as a toolkit for learning, is that instead of hard coding the ReLU activation function here, I've created a pluggable architecture. I've created an activator class, and I've subclassed that to a ReLU activator, to a Logistic Sigmoid activator, that other one we saw before, the hyperbolic tangent, a softmax, and I've got an exotic one in there too, which changes the loss function. So you can experiment with different activation functions to see how that affects the learning. And there is one which is quite cool, which I'm going to put in there now, which is an exotic one called a softmax activator with cross-entropy loss. This actually modifies the mathematics is really complicated, but the algorithm is actually quite simple. So this actually modifies the loss function. So you know when we were squaring the loss to punish the big errors more, turns out you can actually go kind of further with that. You can go even more elaborate in how you accurately measure the loss so that to give it the best result. So I'm going to run this through now, 100 neurons, and while this runs, I'm going to touch on another point, which is about gradient descent. So if we do a gradient descent on this curve, we're going to end up in that bottom well. Now, the curves don't normally look like that, in that if you imagine you're doing a gradient descent on the combined loss for every training sample, it's going to be a complex, wiggly curve. It might end up looking like that. So we can see if we came in from the left, we'd get stuck in a local minima here. And it wouldn't end up with a very good result, right? So this is one of the reasons why I said we initialize the weights and values to the weights and biases to small random values, because by running it again, each time you run it, it's going to start from a different place. So that way you can partly get around this problem by rerunning your training over and over, and each time it will have a different starting place. Having said that, if you do keep your networks relatively simple with your activation functions and the number of layers, what tends to happen is that all those minimas are quite close to each other. So you end up with a situation like this, where if you started from the right, you'd only get a slightly better outcome than if you started from the left. So let's flick back to the training and see how well it's doing. So you can see now it's up to 99.8% accuracy. So are we going to hit 100? This is a really good activation function, and it is slower than a ReLU, but here we are, we got 99.8% with the training data, but we only got 97.9 with the actual test data. And that's no better than we would do if we used a straight ReLU. So this exotic activation function and loss calculation has done a lot to bump up our training accuracy, but it hasn't actually helped with the real-world test accuracy. And this condition is called overfit. It's when it's done a really good job with the training data and it's locked onto a lot of specific features of that training data, but it's unable to generalize well to data it hasn't seen. That's called overfit, and that's what we've got here. We would actually be just as well off with a straight ReLU. And now one other point I'll mention is what to do if you don't have much training data. So I said that we need tens of thousands or up to millions. We already touched on that trick of data augmentation where we can kind of scale and shift and add some noise to the data before putting it in. But there's something else that you can do when you don't have much data. So imagine we didn't have that big set of digits. Imagine we only had a few thousand of those. But imagine that we did have a big set of letters from A to Z. What we could do, we could train it on the letters from A to Z if we had 50,000 of those. And then once we've got that nicely trained, we can then take that and we can use that as a starting point to train the digits, which we've only got a few of. And the fact that because letters and digits are kind of got things in common, it will actually, that's called pre-training, it will actually get a better result. So rather than starting off with random weights and biases, you start off with a network that's already been trained on some other data that is kind of similar, that's got stuff in common, because a lot of those weights and biases encode kind of features, like, you can think of it as encoding the curves or the straight lines and so on, and these things are in common. That's a really good trick as pre-training you can use. There's something else I should also mention, which is what we want to do if we want to take this to the next level, because to get above 99% is quite difficult with the architecture we've got. And also the architecture we've got wouldn't be so conducive to really large complex images. So if we had something like a photograph with a furry animal in it, and we want to train it to find the furry animal and tell us if it's a cat or a dog, we need something that's more powerful than this. And essentially what we need to do is, with this neural network, this is a general purpose neural network that could solve any kind of problem. But what we can do to make it work better is say, look, we're just going to make this work only for images. So if we're going to design this network just for images, we can do tricks like we can put filters and feature extraction filters into the start of that neural network. So it does things like edge detection, or it does things like find curves or straight lines, and then it feeds those features into the inputs of the neural network rather than feeding the raw pixels. So the question is then, how do we write those feature extractors, and then how do we decide on what features to extract? And this is where it kind of gets quite cool, because what you can do is you can write an image processor, but by writing a matrix of numbers and then scanning that matrix over the image, like doing a dot product, you can then do a transformation on it. In other words, you can describe a transformation purely as a bunch of numbers. Now, given that you can describe an image transformation or a feature extraction just as numbers, we don't have to come up with the numbers. We can get the neural network to optimize those numbers. Right? We can get that backpropagation algorithm to work out what are the ideal numbers to extract features. So it will work out what features to extract. We only need to decide on how many layers we want. We don't need to decide on what those layers will extract. Right? That's called a convolutional network. Convolutional layer does a feature extraction and image processing, and then feeds that extracted layer into the next layer. So if you're using the libraries, one of the more powerful features, you'll see options for convolutional layers. And they're really aimed at image processing, and they're also conducive to having lots of layers, and they're very conducive to pre-training. So you can actually load up pre-trained convolutional image networks, which have been trained with millions of images over the internet, and use that as a starting point for doing image recognition. So I've covered, I think I've covered pretty much everything now. Are there any questions?
About the image to start with, you've only got 20 neurons in that first layer, so you're dividing them up into squares or something?
Okay, so when we started out with 20 neurons, I'll bring that up again, I'll put 20 back in there. So there's a couple of points here, but this is just showing you the hidden layer on the left and the output layer on the right. So what we can't see on here is that there are around 780 input cells. They're not neurons, they're cells. And they're also all the interconnections between those and the hidden layer, because if we drew them, there'd just be too much clutter.
I'm confused about the training rates. How do you define the optimal training rate?
Okay, that's a good question. How do you define the optimal learning rate? And there is kind of no silver bullet. You just experiment. You try and different values and see how it works. And what you discover is also that the same value doesn't work well in every layer. So in fact, with this network, I increase the learning rate with every layer as you go to the right. And that's actually commonly done. You need a higher learning rate as you go to the right. And also, I decrease it slightly with every epoch as it becomes more accurate. And so you have to be careful with the learning rate, because when you start modifying other aspects of that, so you change, for instance, the activation function, then you might also find you need to change the learning rate. If you don't do that, you get a really bad result, and you assume it was that new activation function was no good, when in fact you just needed to change the learning rate to match that function. But yes, it's just kind of trial and error, and there are, in the heuristics. So some of the more advanced networks will kind of work it out themselves, that they've got heuristics to work it out. And there even are adaptive learning rates, I believe, where it will actually train itself into the right learning rate. Yes?
When you're doing your back propagation, rather than just feeding it into the next level up, could you feed it into all the levels up?
Okay, this so that you mean by up, you mean to the left?
To the left.
To the end? Okay. You could try that. I don't see how that could improve it though, because but by weighting working out the output votes as a weighted sum of the input votes, that seems to capture everything that. All it would do is it would kind of leak some dirty data back towards the input, because when you feed from the output to the first hidden layer, the hidden layer itself will give the best possible feedback as to what the layer to the left of that would need. So I'm not sure that would help, but that's just from a really quick 10-second evaluation, because there might be some subtle reasons why that could work well. I do know that when it comes to feeding forward, it can actually sometimes help to allow stuff to leak forwards, because it can help when with training very deep networks that would otherwise not quiesce. So there are subtleties like that, which often they are discovered by trial and error.
So the input layer has intrinsic meaning, the output layer has intrinsic meaning. The hidden layers in the middle, do those have any intrinsic meaning?
That's also a good question. And no, they don't. They mean something to the neural network, right? But they don't. It's very unlikely that it means much to us. It's very hard for us to look at what's in that layer and try and correlate that's got something that's meaningful to us. It's unlikely, because it does represent some kind of extraction. So if you think about the digits, it could be capturing the concept of a loop or a concept of a straight line or something, but that's way too simplistic. It's probably it's more complex and subtle, and it's unlikely that we would find much, at least with this style of network. It's possible with convolutional networks that we might see something that was more meaningful to us. But yes, it does have meaning, but I don't think it's something that would mean anything to us as humans.
You mentioned earlier that you'd be better off just having a taller network rather than a wider network.
Yes.
For example, in what scenarios does it best have more neurons versus more hidden layers?
Well, this scenario certainly is better to be taller. If you're using convolutional layers, that's very conducive to having more layers rather than just being taller. And also with convolutional layers, and this may also apply to other architectures, they're not fully connected. So what's one of the advantages is that with that kind of image processing you're doing is before it feeds into the network, in a sense, is that if you think of the whole thing as one neural network, the neurons in the input layer won't all of them will be connected to every neuron in the next layer, and that makes the convolutional networks more efficient. And I think that also probably, my intuition is that helps with the depth, allowing for more layers. But really the best way is to, with this kind of thing, is to try it and see. And don't give up too soon. If it doesn't work, try a different activation function in there, or changing the learning rate, or but the best way really is to experiment and see.
Is there the possibility of having multiple activation functions?
You mean across layers?
Yeah.
Yeah, definitely. What we just did, we were using the softmax activation function in the output layer. Here. So this and then the ReLU in the hidden layer. And that's quite often done, is that you have different activation functions in different layers. That's quite very common.
So far, you have discussed about inputs is binary data. So what if you have different data for the input, like not 0 and 1?
Okay, so in this case, well, actually, it was fractional. Well, yes, it was numbers. The input data in this case was between 0 and 255, because that was how I was representing the pixels. Right, there was a grayscale. So you basically convert it to a number, a real number, and then that becomes your input.
That's when we need to normalize the data before feeding into the network.
Yes, you need to. I believe it has to be at some kind of number before that, and also that the way in which you convert it to the number can have an influence on how successful it is, because you're effectively doing some pre-processing, which can make it much easier or harder for the network, depending on how you do that. Okay, I believe we've got time maybe for one more question, and then call it quits.
Hey Joe, having never dealt into neural nets, this explanation was lucid enough for me to get a grasp of things. You've given us an example to play with. What do you expect we can do as the next step up to try and apply this knowledge?
I suggest you download that and just have a play with it, fiddle with it, or even you could just write that first example again from scratch. That would be the first thing I would suggest you do, is take the simple example we had with one neuron to do the NAND gate, and start again. See whether you can reproduce that, because if you can, you pretty much understand the learning algorithm if you can do that. It's not that hard, but that's the first stage, because what you'll probably find is if you do a clean room implementation of that, it won't work. You'll get some basic thing wrong, and that's how you learn. That's how you get that. I did this myself. I thought it was simple. I wrote it. It didn't work. And I realized I didn't really understand how it worked. And that I believe is the first step. Now, the next step, if you want to have some more fun with this, is you could experiment with different activation functions. It would be really cool if you wrote a convolutional layer for this. If you do that, please send it to me. Okay, thanks everyone. So yeah, that's all we've got time for. Thank you for coming.